Hello, relativity friends. About a year ago, I made a video called Deep Dive into the Metric, the Tensor. And I've gone back and looked at it a couple times, and it's really not very good. I think I can do better, and that is the goal of this, to do better than the last one. So let's start with the question: what is the metric, the tensor? Metric tensor is a mathematical object used in differential geometry to define distances and angles within a given space. Okay, well, that's good, but what is differential geometry? Differential geometry is a mathematical discipline that studies the geometry of smooth shapes and smooth spaces, otherwise known as smooth manifolds. All right, we got that. What are some of the branches of differential geometry? Well, here's some: Riemann geometry and all the rest of these. I don't know what they are. All right, so what is Riemannian geometry? Riemannian geometry studies Riemannian manifolds, smooth manifolds with a Riemannian metric. Well, what's a Riemannian metric? The metric tensor. Boom, full circle. So, when Einstein wanted to develop his theory of general relativity, he had a concept that it would be in a curved space, and he needed something in that curved space to measure angles and distances and areas and volumes. So that's why he chose Riemannian, the geometry, because it has the metric, the tensor, and the metric tensor can be used to study real physical things. So that's the whole point of it. All right, let's look at the Einstein, the field equation. Okay, we've got all this stuff on the left and some stuff on the right. The stuff on the left is the geometry, the part. So this is about the curvature of space-time, and the stuff on the right is the stuff in space, energy and matter and me and you and comments and star, everything. This is all stuff, and this is all about how this stuff makes space-time curve, okay? So what we have here is these are tensors, this one, this one, this one, and this one. This is called the Ricci, the tensor, Ricci, the scalar, the metric tensor, the cosmological, the constant. This is the dark matter, the thingy here, which is unbelievable to me. Once again, the metric, the tensor. All right. So the Ricci, the tensor, was named after Gregorio Ricci Cubrastro, a handsome lad. Who is the father of tensor calculus? Tensor calculus is the language of differential geometry. So that's why we study this stuff. It's complicated, but if you don't know the language, you can't study the math. So that's the point. And the Ricci tensor is actually a reduction of the more general Riemann tensor, which is this frightening looking thing. And you guessed it, it was named after Bernhard Riemann, another handsome lad, the father of Riemannian geometry. I guess that's obvious since his name's Riemann. Okay, so we want to take just a quick look at the Ricci, the tensor. Oop, I cut her off. That's all right. We can still do it. So the space-time has 4 dimensions. There's 1 temporal dimension, time, and 3 space, the coordinates. So there's 4 the coordinates, which makes this a 4 by 4 or 16 separate entries. And it is a symmetric, the tensor. So that one's equal to that one, this one's equal to that one, this one's equal to, etc. So there are, if you go down the diagonal, so it's symmetric about the diagonal, there are 10 unique here and here. There are 10 unique entries, and these are repetitions of that into this. And these entries here are functions of this object, which is called the Christoffel, the symbols. And the Christoffel, the symbols themselves are a function of the metric, the tensor. So everything starts with the metric, the tensor on the left side of Einstein field equations. The curvature of space-time, you have to have a metric. in order to do anything, because you have to put it into the Christoffel symbols. You put the Christoffel symbols into the Ricci tensor, or actually into the Riemann tensor, but that's not important, in order to solve the left side of that equation. All right. So let's get rocking on what this thing can be used for. Okay, we all know that a vector can be written as a linear combination of its components and basis to vectors. Now, let's work in 2 dimensions to start with. The two-dimensional Cartesian, the coordinate is given as just, it has an x component and a y component, right? And it has these unit the vectors, I hat and j hat. It could be x hat, y hat, ex, ey. Any way you want to write it, excuse me, it all means the same thing. So they're basis vectors of unit length, they're 90 degrees apart, and they're called orthonormal basis vectors. All right, let's look at some examples here. All right, so here I've drawn our basis vector. So here's I hat. It's 1 unit long in the x direction, and j hat is 1 unit long in the y direction. And you notice they're 90 degrees apart. Now I can define vectors by using this notation. As an example, this vector p, I would go 1, 2, 3 I hats up 1 j hat. That defines this vector. I could do this other one, v, which is 1, 2 I hats and 1, 2 the j hats. And there's also an angle between these, okay? Now, and you know how to add these. You would just, if you wanted to add these 2 vectors together, you would say 3 I hat plus, I'm sorry, 2 I hat plus 3 j I hat would be 5. So you go out 5, and then you'd go up 2 plus 1 is 3, and that would define the addition of these 2 vectors. Or you could subtract them. But what we want to talk about is multiplying these 2 things together, which is called the product. It has many names: dot product, inner product, the scalar of the product. It takes 2 vectors, multiplies them together, and produces a scalar being just a number. Okay? So here's the way we were taught in school. We got 2 vectors defined with these unit vectors. We want to multiply them together. So what we do is say it's 2 times 3 plus 2 times 1 is 8. So the dot product, the scalar product of these 2 vectors is 8. Okay, well, that's the right answer, but it's for all the wrong reasons. Because the product, enter the product you're doing here, it only works in Cartesian coordinates with orthonormal basis vectors. And in relativity, you work with curvilinear the coordinates that do not have this. They do not have orthonormal basis to vectors. Sometimes they have ortho the basis vectors, but I don't think they ever have orthonormal basis vectors. All right, so let's look at how this really is. So you've got 2 things here added together times 2 things added together. Well, just think of these as when you're in algebra, these are 2 polynomials, right? Well, you should have 4 terms. If you go first, outer, inner, and last, you should have the 4 terms, and you do have 4 terms. Looks like this. Now, since these are just scalars, they're just numbers, I can pull those outside of the dot products, and it looks like this. So here's my 4 terms. All right, now what is the definition of the dot product? Here's one of them. You say the dot product of 2 vectors is the magnitude of the vector times the magnitude of the other vector times the cosine of the angle between them. Now, what's the magnitude? Well, it's just from the Pythagoras theorem. We can look at this. Do you see this? This would be the hypotenuse of this right triangle right here. Do you see it? So this length squared is equal to this length squared plus that length squared. So that's what the magnitude is. All right. So let's take some of these dot products and look at it using this definition. So we would say I hat dot I hat. Well, what's the magnitude of I hat? Well, it's 1. We said it was. It's just 1. What's the angle between them? Well, they're on top of each other. So it's 0. Well, what's the cosine of 0? 1. All right, so I hat dot I hat is equal to 1. Now, what about a cross term? What about I hat dot j hat? Well, the ortho and orthonormal means that I hat and j hat are right angles to each other. So we do that same thing. We say we got 1 and 1. What's the angle between them? It's 90 degrees. What's the cosine of 90 degrees? 0. So our our 4 terms look like this. These two cross terms, I hat, j hat, I hat, they go to 0. So you get the same answer as you did with the shortcut. But the point being, this is how you do it. And this is the tensor for the Cartesian coordinates in 2 dimensions. You get a 1, a 0, a 0, and a 1. This is called the identity matrix. It looks like that. So the dot products in matrix form would be, this is my first of the vector times the identity matrix times my second the vector, and the answer is 8. So the generalized form of the product, enter the product, in any the coordinate system would be this. It's given by the sum of the tensor over these two components to ever how many dimensions you have times the components themselves, right? So in our case, that we just had 2, so there's just G11, V1, the P1, G22, V2, the P2, right? So it's that simple. Now let's do something a little bit more complicated. Let's derive the metric tensor in spherical the coordinates. Okay, so here's what we're going to do. We have a vector. Excuse me. And we've superimposed this on a three-dimensional Cartesian frame, x, y, z. And we have an angle here that defines how far this vector is from the north of the pole. That's the theta. And we have a projection of that onto the xy, the plane. And this angle phi is how far that projection is away from the equator. So we have 2 angles and 1 length. And if you stare at these long enough, you'll see where these 3 definitions come from, okay? Because here's one right angle, here's another right angle here, and here's another right angle there. So that's how we get x, y, and z in terms of r, theta, and phi. All right? So now we can write this vector as the x component, the y component, and the z component with our orthonormal unit vectors in 3 dimensions. Now what we want to do is we have this r value now is a function of 3 variables, r, theta, and phi. And to find the metric tensor, we need to find the basis of vectors in r, theta, and phi. And we're going to call those ER, E theta, and E phi. Now, to find the basis of vectors, what we need to do is differentiate this with respect to the different the coordinates. And that's called directional derivatives. So we're going to take the directional derivative of that vector r with respect to the coordinates. So we're going to get 3 separate things. ER is the partial derivative of that vector with respect to r, and likewise the theta, and likewise the phi. Okay? So we just got to differentiate all these. And you remember how to do partial differentiation. You're differentiating something with respect to one variable. So everything else is held constant. So in this case, the derivative of r is just 1. And these are constants because they don't have r in them. So you just write them down. The same thing here, you write it down. The same thing here, you write it down. All right, now let's do theta. Well, this time r and cosine phi are the constants. So you just write those down. And the derivative of sine the theta is cosine theta here. And here, the r and the sine, the phi are constants, and derivative of sine is cosine. Here, r is a constant, derivative of cosine is minus sine. All right, we do the same thing with phi, and we get this. Now, the last term, there's no phi in it, so it's just a 0. Okay? Now, To find the metric tensor, we have to find the product of all these basis to vectors. All right, so we're working in 3 dimensions. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to have 9 entries into this. And it is the dot product of all of these different basis to vectors. Okay, so let's start with the first one, ER. So we write down what ER is, and we found it to be this. We dot it with itself. We come out with this expression here, and you see the first thing we can do is factor out a sine squared the theta. That leaves a cosine squared phi, sine squared phi. You know this identity is 1, and that leaves then sine squared theta, cosine squared theta. That identity is 1, so it's just equal to 1. So the first entry in the spherical, the coordinate metric tensor is just 1. Now let's do a cross term here, okay? Let's do ER dot E theta. So we go up above, we get our ER, we get our E theta. We do this, the multiplications, and we can factor out of here, let's see, R sine theta cosine the theta. Yep. So what's that leave? That leaves a cosine squared the phi and a sine squared phi right here, sine squared the phi. And here it leaves a -1. Well, this is 1. This is a -1. So that goes to 0. So I'm not going to show it, but all of these cross terms, this one, this one, this one, this one, this one, and this one are 0. So only thing that survives is the diagonal. All right. Now the tensor is a symmetric tensor. So when you find that this one is 0, then you know that one's 0. When you find this one is 0, you know that one is 0, etc. But all of the cross terms are 0. I'm not going to do each one of them because it's a lot of work. You got to trust me. All right, so we did a cross term. Now let's do the theta. All right, it's the same thing. You just keep factoring things out until you get down to one of these identities, just like I did here. This is 1. So g theta is r squared. And phi goes exactly the same route. We get down to one of these identities, which is 1, and we're left with r squared sine squared the theta. So our metric tensor in spherical coordinates is, on the diagonal, 1 r squared sine the theta, and all the rest of these are 0. Okay? Now, what can we do with this? I'm going to put a link in the description where we actually take this, we set the radius to 1. We set it to, I'm sorry, not 1, a constant. We just say it's a constant. And we use that to calculate the Riemann curvature. First of all, we calculate our Christoffel, the symbols. Then we calculate our Riemann, the curvature tensor. Then we calculate our Ricci tensor. Then we calculate our Ricci, the scalar. So all of that is done on the surface of a sphere. It's called intrinsic, the curvature. I'll put a link to that if you want to know more about how to use this. All right, now we're going to do something called the arc length. So let's go back to our Cartesian space, and we just put a vector in here, right? It's just like sticking up somewhere. Well, this vector goes from point 1, 1, 1 to 3, 3, 3. So that's XYZ, XYZ. So the magnitude of this vector would be the Pythagorean theorem in 3 dimensions, right? So it's just a change in X, a change in Y, the change in Z. So that would be 3 minus 1 and 3 minus 1 and 3 minus 1. So there's 3 of those. So 3 minus 1 is 2, and 2 squared is 4, and 3 times 4 is 12. So the magnitude of this vector is the square root of 12, right? Now we can also carry this out into what's called an infinitesimal. And if you think of this, now this would say this is some arc length. If you look at a curve and you zoom in close enough, you just keep zooming, you will find a piece of that curve that looks flat. And that's what this means. This means that you're looking so close that you can define the section of that curve as a straight line. Not a straight line, a triangle that you can do this calculation on. So this is called the infinitesimal arc length. Now we're going to convert this into spherical, the coordinates, all right? So we substitute in our x, y, and z from our spherical, the coordinate, the diagram. And here, I'm going to let the theta equals A and phi equals B. And the reason I'm doing that is because what I'm doing here is the Google Docs equation editor and continuing to write these. It's if you ever use it, it's a pain in the ass, but that's all I got. All right. So here is our coordinate that transforms into r theta and phi, in this case, r, a, and b. Now I got to differentiate these because we're going to do this, okay? And children, do not attempt this at home. It is very painful. This is very, very long. So we have here three variables multiplied together. So this is just a multi-product rule. So we take the differential of this, write these two down, take the differential of that, write this down, take the differential of this and write these two down, right? So that's what I've done here. So the differential of r is just dr. I write these two down. Then I write down r cosine b. Now I'll take the differential of sine a, which is cosine a dA. All right. So that's what all of these are. I just do the same thing each time until I get these three things. Now, the next thing I have to do is to square them. Now, all of these cross terms go to zero. You got to trust me on this. It is an absolute mess. You can sit down with pen and paper and prove it yourself, but they all go to zero, right? So what I'm going to do is just square each one of these inside here. Instead of the cross terms like dr with dA and dr with dB and dA with dB, etc., they all go to zero. I swear they do. Because I know the answer. All right. So I take this first one, I square it. I get dr squared, sine squared A, cosine squared B. I square that one. R squared, cosine squared A, cosine squared D squared, et cetera, et cetera, et cetera. I just keep doing this, right? So now I have this. So now what I got to do is add all these rascals together. And at the same time I add them, I'm going to gather up these cross terms. I mean, these similar terms. So I got a dr squared, dr squared, dr squared, right? So I'm going to do it like this. So I got a dr squared times this expression, dA squared times this expression, dB squared times this expression. Now you just keep reducing these until you start getting those identities, right? So you see right here, I got a cosine squared B plus sine squared B. Well, that's just 1. And 1 times this is sine squared A. Sine squared A plus cosine squared A is just 1. So that's just going to make this a 1. And now I do the same thing here. And I just wind up with an r squared. I do the same thing here, and I wind up with r squared sine squared theta. So the answer is ds squared equals dr squared plus r squared d theta squared plus r squared sine squared theta d theta squared. This is called the infinitesimal line element. Now, the one thing you notice is this is exactly the same thing we got on the diagonal of our metric tensor. We got a 1, we got an r squared, and we got an r squared sine squared theta. So that means you can write it like this. The infinitesimal line element is equal to the metric tensor times the derivative of the coordinates multiplied together. Because that's exactly what this is, right? So this is GRR right here is 1 times the dr squared. This is G theta theta is r squared d theta squared. That's here. And d phi phi is r squared sine squared the theta, the dx, the d phi squared. So that's exactly what that is. All right. So I hope that was better than the last one and that you find it useful. If you want to know more, make sure you go up where I said there is a video link in the description. You're going to get a whole dose of it right here. if you're interested. All right, thanks for watching. I'll see you later.